Welcome! Today, we'll learn how to solve inequalities involving two functions, like f(x) less than gx or f(x) greater than or equal to gx, using a graphical approach. The first step is to plot the graphs of both functions y equals f(x) and y equals gx on the same coordinate plane. Step 2 is to find the points where the graphs intersect. These are the x values where f(x) equals gx. These intersection points divide the x-axis into different intervals, which we'll examine next. Step 3 involves comparing the graphs within each interval. Where the graph of f(x) is vertically above the graph of gx, we have f(x) greater than gx. Conversely, where the graph of f(x) is below the graph of gx, we have f(x) less than gx. Finally, step 4 is to write down the solution set based on the inequality. For f(x) less than gx, identify the intervals where f is below g. For f(x) greater than gx, identify the intervals where f is above g. For inequalities with or equal to, like f(x) less than or equal to gx, remember to include the x values of the intersection points in your intervals. Let's work through an example. Suppose we want to solve inequalities involving f(x) equals x squared and gx equals x plus 2. First, we plot both y equals x squared, a parabola, and y equals x plus 2, a line, on the same axis. Next, we find the intersection points by setting x squared equal to x plus 2. Rearranging gives x squared minus x minus 2 equals 0. Factoring, we get x minus 2 times x plus 1 equals 0. So, the graphs intersect at x equals minus 1 and x equals 2. Now, we compare the graphs in the intervals defined by these points x less than minus 1, x between minus 1 and 2, and x greater than 2. For x less than minus 1, the blue parabola, x squared, is above the red line, x plus 2, so f(x) is greater than gx. Between x equals minus 1 and x equals 2, the blue parabola is below the red line, so f(x) is less than gx. For x greater than 2, the blue parabola is again above the red line, meaning f(x) is greater than gx. Finally, we write the solutions. f(x) is less than gx on the interval from minus 1 to 2, excluding the endpoints. f(x) is greater than gx on the intervals from minus infinity to minus 1 and from 2 to infinity. For f(x) less than or equal to gx, we include the endpoints, the interval from minus 1 to 2, inclusive, and for f(x) greater than or equal to gx, we include the endpoints, minus infinity to minus 1 inclusive, union 2 to infinity inclusive. To summarize, here's a table showing what to look for on the graph for each type of inequality. Solving inequalities graphically is a powerful visual tool. By plotting the functions and comparing their positions, you can easily determine the intervals that satisfy the inequality. Thank you for watching. Welcome! In this video, we'll tackle a problem involving absolute value and linear functions. Part A asks us to draw the graphs of y equals 5 plus the absolute value of 3x minus 2 and y equals 11 minus x. Part B asks us to use the graphs, or otherwise solve the inequality. 11 minus x is less than 5 plus the absolute value of 3x minus 2. Let's start with Part A, graphing the functions. First, we'll set up our coordinate axes. Let's graph the linear function. y equals 11 minus x. This is a straight line. Its y-intercept is 11, which means it crosses the y-axis at the point 0, 11. Its slope is -1. Let's draw this line in red. Now, let's graph the absolute value function. Y equals 5 plus the absolute value of 3x minus 2. This graph will have a V-shape. The vertex, or the tip of the V, occurs where the expression inside the absolute value is 0. So, we set 3x minus 2 equal to 0, which gives x equals 2/3. When x is 2/3, y equals 5 plus the absolute value of 0, which is just 5. So the vertex is at the point 2/3, 5. For x values greater than 2/3, the slope is positive 3. For x values less than 2/3, the slope is -3. Let's draw this V-shaped graph in blue. Now for part B, solve the inequality 11 minus x is less than 5 plus the absolute value of 3x minus 2. Graphically, this means we are looking for the x values where the red line, y equals 11 minus x, is below the blue V graph, y equals 5 plus the absolute value of 3x minus 2. To find these regions, we first need to find the points where the graphs intersect. We set the two equations equal to each other. Let's solve this algebraically. First, isolate the absolute value term. Subtracting 5 from both sides gives 6 minus x equals the absolute value of 3x minus 2. Now, we consider two cases based on the definition of absolute value. Case 1, the expression inside the absolute value is positive or 0. So, 3x minus 2 equals 6 minus x. Adding x to both sides gives 4x minus 2 equals 6. Adding 2 gives 4x equals 8. Dividing by 4 gives x equals 2. Case 2, the expression inside the absolute value is negative. So, negative 3x minus 2 equals 6 minus x. This simplifies to minus 3x plus 2 equals 6 minus x. Adding 3x to both sides gives 2 equals 6 plus 2x. Subtracting 6 gives negative 4 equals 2x. Dividing by 2 gives x equals -2. So the graphs intersect at x equals -2 and x equals 2. Let's mark these intersection points on our graph. At x equals 2, y equals 11 minus 2, which is 9. Point is 2, 9. At x equals -2, y equals 11 minus -2, which is 13. Point is -2, 13. Now looking back at the inequality, 11 minus x is less than 5 plus the absolute value of 3x minus 2. We want the x values where the red line is below the blue V graph. Observing the graph, this happens when x is less than -2 or when x is greater than 2. Therefore, the solution to the inequality is x is less than -2 or x is greater than 2. We have successfully graphed both functions and solved the inequality both algebraically and by interpreting the graph. The solution confirms the regions where the linear function lies below the absolute value function.